This video is going to go over two examples of a synthesis reaction. You all need to be aware that a synthesis reaction typically takes place when you have two elements or two compounds interacting with each other to make a more complex compound. The first example is iron 3 reacting with sulfur. So the first thing you guys need to do is translate that into the abbreviated formulas to write the reaction. Iron plus the sulfur really the only thing it can make is the iron teaming up with the sulfur. Now, right now it's just solid iron and solid sulfur. So when they team up together, you're going to have to charge balance this as it is an ionic compound. What version of iron is it? It's iron 3. It does not mean there's 3 irons. It means that the version of iron we have is charged plus 3. Sulfur on the periodic table is a -2. Now, in order to charge balance this, you guys got to kind of find a common multiple that the 2 and the 3 goes into. Most times you guys say 6. In order to make this sulfur a 6 negative charge, you would need to have 3 of them in the subscript. In order to make the iron a positive 6, you need to have 2 of them in the subscript. Now that the iron 3 sulfide, if you wanted to write that out, now that it is charge balanced, you need to go through the whole reaction and make sure you have enough atoms or particles in the whole reaction to make this thing work. For a synthesis reaction like this is simple. You don't necessarily need to do the little T-chart where you count them up on the reactant side and the product side. I can see that the iron is so low on the reactant side and so is the sulfur. That's usually an easy fix because any coefficient out front doesn't affect the other one on this side. So on the right hand product side, I have 2 iron. I'm simply going to put a 2 up here for the coefficient. Since I have 3 on the product side, I'm going to put a 3 in front of the sulfur. And now I have all the particles I need. If an assessment or a worksheet ever asks you guys to draw the particle diagrams, make sure you draw the particle diagrams below, just to account for mass, the idea of conservation of mass. And then you would draw sulfur 3 times. And here we're not worried about the diameter or the radius of the particles, and so on. Also make sure if the directions or the test ask you to add up all the masses for the elements and the compounds, make sure you do that and leave the coefficients out of it. But over here for the iron 3 sulfide, you would want to include the subscripts in your multiplication. So just for example, you would want to find on the periodic table the mass for a package of iron, which is approximately 55.85. And since this 2 is a subscript, we want to go ahead and account for that and take it times 2. And then you would want to find the sulfur at 32.07. Since there's 3 of them, take it times 3. Eventually, you would multiply those and add them all up, and this would be the mass for the whole package of iron 3 sulfide. And you could use this for a unimultiplier to make predictions later on. I'm going to do the second equation down here with a prediction with iron 3, oh, excuse me. The second example I was talking about is actually hydrogen gas reacting with nitrogen gas. Now, even though these seem to be both nonmetals, do not forget that hydrogen has the ability to be a +1 or a -1. So it can still become charged, and so can nitrogen, and it can team up to make a positive and negative ionic style compound. But first, start by interpreting the statement into the actual formula compounds. Remember that hydrogen is one of the gases that is satisfied when it teams up with another hydrogen and becomes diatomic. Nitrogen is the same way. Based on the Lewis structures we've previously done, nitrogen likes to team up with another nitrogen to fulfill the rule of 8. So the only thing that hydrogen and nitrogen can do is combine. And if we imagine that they both become charged, people will often write nitrogen first, then the hydrogen. Now, if we imagine they're charged, hydrogen in this case is going to be a +1 because nitrogen is on the non-metal side of the periodic table, and it is a -3. Now that I've got my prediction written out, the first thing I need to do is charge balance it since it is acting like an ionic compound. I simply have one positive charge of hydrogen, so I need a subscript of 3 to cancel out and balance out the -3 of the one nitrogen. The simple name for this is often called ammonia. Some people might list it as nitrogen trihydride, which follows a blend of the molecular naming rules. So there's a couple versions of this floating around if you look it up. Now that I have it charge balanced on the right-hand side, I need to go back and make sure I have all the atoms I need to make this equation work from a conservation of mass point of view. I'm going to go ahead and look at the compound over here on the product side because the reactants are so low individually by themselves and they're easy to fix with a coefficient. So on the right-hand side, I see I have 3 hydrogen, but on the left-hand side, I have 2. So I know I'm going to have to do a multiplication here somewhere. So I might start off with the nitrogen and see how I can easily make it balance out. So if I throw a 2 in front of the nitrogen on the product side of the ammonia, that takes care of the 2 nitrogen on the left. But then we have to look downstream and see what that effect has on the hydrogen. Since I have a 2 out front, that means I technically have 6 hydrogen total in the products. I only have 2 in the reactant side. So now you guys got to think about some kind of common multiplier here that they both end up in some kind of common factor of 6. And then that makes this an easy fix by putting a 3 out front of the hydrogen. Now we have 6 hydrogen on the reactant side and 6 hydrogen on the product side. So now it's fully charged balanced and mass balanced. Now I'm going to do a prediction using the equation and unit multipliers along with the package masses of each compound and element. So my statement on the right side of the screen says predict the amount of hydrogen gas needed to produce 300 grams of nitrogen trioxide. Or ammonia, which is the way I was writing it versus the other versions you might see online. Well, that's actually not correct. Hold on. Okay, I fixed the spelling error. It's trihydride is one version you guys might see on the internet for this compound. So predict the amount of hydrogen gas needed to produce the 300 grams of this product. So that's imagining you want 300 grams of this product. Now you need to find out how much hydrogen gas you actually need to make this thing produce that much ammonia. So technically, the first thing you guys would want to do is add up all the masses for all the element packages, and I'm going to review that with you and my expectations. So I'm not worried about the coefficients till later. I'm going to deal with just the subscripts. If you look on the periodic table, you'll see the hydrogen is approximately 1.01 grams. But since there's two of them, I'm going to take it times 2 because I want to know what the mass is for a whole package of hydrogen gas, and hydrogen gas is diatomic. I'm not going to worry about the 3 for the coefficient. That's going to come out later. So if I multiply those, you should get 2.02 grams of H2. But now I'm going to bring down that coefficient. This is going to be a potential factor I can use in my ratio building for the unimultipliers. And now for nitrogen, I'm going to do something similar. If you look on the periodic table, nitrogen should be approximately 14.01 grams. I'm going to take it times 2 since it's diatomic. No coefficient this time. And if you take that and multiply it out, you should get approximately 28.02 grams of nitrogen gas. This also could be a factor I use to make a ratio. And then finally, I'm going to get the package mass of one compound of ammonia. I have 1 nitrogen if I ignore the coefficient. Again, I just want to get how much is one package of ammonia. But I have 2 in the recipe. I get that. I've got hydrogen at 1.01 grams, but it's times 3 because there's 3 in the subscript. If we multiply and add those all up, we should get 17.04 if my calculations are correct. And I'm going to bring down that coefficient. So the 17 grams is how much one package of ammonia has for mass. The 28.02 grams is how much a package of nitrogen diatomic gas has. The 2.02 is the mass for a package of H2 diatomic hydrogen. And then I've got the coefficients on the front as multipliers. Now I'm going to build my unimultiplier. Remember the mantra for a unimultiplier, you start with what you have. So I have 300 grams of ammonia that I want to produce. So I'm imagining that. Now I need to use the package masses with coefficients as needed to cancel out the grams of ammonia to get back to the hydrogen. So I know from the reaction that I need 2 servings of this 17.04 grams of ammonia. So you need to follow the equation or follow that recipe. So the grams of ammonia cancel. And I want to jump to hydrogen gas. And I know from the reaction that hydrogen gas is the 3 times the mass of one package of 2.02. And so the units I end up with is grams of hydrogen, which is what I wanted on the outcome. Now I'm going to go through some simplification steps. If you guys take the 300 grams and multiply across, you'll get the numerator we need. I'm going to go ahead and multiply across the top. And you guys should get, if you want to try this on your own and double check me, 1,818 grams of hydrogen. I got to clean up the denominator. 2 times the 17.04 grams should be approximately 34.08. No units because the units got canceled. And now you need to show your work for simplifying this. If you divide the 1,118 grams of hydrogen divided by that 34.08, you should get approximately 53.3 grams of hydrogen gas. So if you did want to produce 300 grams of ammonia, you would need to have 53.3 grams of hydrogen and hope you get 100% completion of the reaction.